Good afternoon, students. Good afternoon, JNV Ramnagar students. Can you able to hear me? Am I visible and audible? Okay, okay. Fine. Good. So let's continue with the equilibrium lesson. Yesterday we have discussed about the chemical equilibrium part, right? And we have studied about the equilibrium constants and what is chemical equilibrium and what are the characteristics and properties of those chemical equilibrium and equilibrium constant, etc. And we have solved few questions, right? Now today we will move on to the ionic equilibrium part of that lesson. So in this ionic equilibrium, the objectives under this are substances and electrolytes and its types we are going to see, and acid-base theories, self-ionization of water, then coming to buffer solution and its types we will discuss there, and at last solubility product and its applications. Okay, so we are going to cover these topics today under ionic equilibrium. Okay, these are the very important topics you have to concentrate in this lesson. So moving on to the first thing, the substance. What are substances? Or substances, they can be classified here into two types. Okay, one we call as electrolytes and the other substance is called as non-electrolytes. So what are the properties of electrolytes and what are the properties of non-electrolytes that we will discuss, and then we will move on to the next topic. Coming to the electrolytes, its aqueous solution conducts electricity. If your substance is an electrolyte, then in its aqueous form, they will conduct, electrolytes will conduct electricity. Okay. And in aqueous solution, what happens? How do a system or a substance conducts electricity? By the movement of ions or electrons, right? So here, ions, due to the movement of ions. So they get dissociated, the substance, the electrolyte get dissociates in corresponding ions on dissolving in water. For example, sodium hydroxide, HCl, NaCl, etc. So these compounds will get dissociated. For example, if I take NaOH, if I take NaOH and if I try to dissolve this NaOH in water, what happens? Sodium Na plus ion and OH minus ion will get dissociated. And due to the movement of these ions, the substance is conducting the electricity. Okay. And coming to the non-electrolytes, it is just the opposite of this electrolyte, right? So its aqueous solution does not conduct electricity. Okay. And they do not dissociate on dissolving in water. For example, we can take sugar, urea, etc. Suppose if I take urea, the formula for urea is NH2CONH2. Okay. This substance is called as urea. It is an organic compound. If I try to dissolve this organic compound in water, you see here, the solid urea is getting converted to aqueous urea. That is the change. So it is not producing any cation or anion. So they will not dissociate or dissolving in water. So those substances are called as non-electrolytes. Now for this lesson, we are going to take electrolytes. So let's study about the electrolytes. So what are electrolytes? Again, these electrolytes are classified into two. Okay. The first classification is strong electrolyte and the second classification is weak electrolyte. What are strong electrolytes? Strong electrolytes are the substances which gets dissociate completely on dissolving in water. Okay. So if I'll give you the examples now within few minutes. So the ions will get dissociate completely. So those substances are called as strong electrolytes. And the degree of dissociation, if we see, it will be approximately equal to 1. So this alpha denotes the degree of dissociation. And for strong electrolytes, it is approximately equal to 1. The examples are sodium hydroxide, HCl and NaCl. Na plus and OH minus, H plus and Cl minus, Na plus and Cl minus, they will get dissociate completely. There will not be any interaction between the cation and the anion. The ionic interaction will not be there on putting this into the water. Okay, and the dissociation almost reaches to completion. So no equilibrium exists. There is no equilibrium. So once if I put this sodium hydroxide into this water, it is getting dissociated, right? So again, the sodium and Na plus ion and OH minus ion cannot come together and form the NaOH again. So product cannot be converted into the reactant back again. So there is no equilibrium existing here in this strong electrolytes. Clear? So any doubt from the strong electrolyte part for anyone? If everything is clear, give me a thumbs up or type yes in the chat box. If you are having any doubt from the strong electrolyte, just raise your hand and ask me. No doubt. Okay. Okay. Good. Thank you, students. So we will move on to weak electrolytes. Thank you. Thank you so much. Yeah. Coming to weak electrolytes, dissociates partially. This term is very important. The partial dissociation on dissolving in water, those substances are called as weak electrolytes. And here, if you see the degree of dissociation alpha, it will be less than 1. For weak electrolytes, it is less than 1. And some of the examples of weak electrolytes are ammonium hydroxide and propanoic acid. Okay, NH4OH and C2H5COOH. So these are the examples of weak electrolytes. And partial dissociation of substance occurs, hence there will be an ionic equilibrium. Suppose I'll show you an example. You see, I'll take ammonium hydroxide. So I have taken this compound and I am trying to dissolve this in water. And here I'm getting NH4 plus ion and OH minus ion. But there will be some interaction between this cation and anion because dissociation is partial, right? So because of that, partial dissociation or because of the interaction between the cation and anion, they can combine with each other and they can form the reactant back again. That's why it is said that the substance occurs, partial dissociation of the substance occurs, and hence there will be an ionic equilibrium. Okay, so here no equilibrium, and here we have the ionic equilibrium. Got it? So this is about the strong electrolytes and weak electrolytes. So most of the strong acids, strong base, or the salt which has been formed from a strong acid and a strong base, they will come under strong electrolytes. You can see here, sodium hydroxide is a strong base, hydrochloric acid is a strong acid, sodium chloride is a salt which has been formed from sodium hydroxide and HCl. From strong acid and strong base only we have prepared this salt, right? So it is also an example for strong electrolyte. All the strong acid base and salt will fall under this, and all the weak base, weak acid, weak acid base salt combination, they will come under this weak electrolyte. Got it? So shall we move on to the next topic? Substances topic and electrolytes topic. These two topics are clear to all of you. Shall I move on to the next? Yes. Good. The next topic is acid-base theory. Yeah. Acid-base theory. So, yeah, in this acid-base theory, we have 3 concepts. The first one is Arrhenius concept of acids and bases. The second is Bronsted-Lowry concept of acids and bases. The third is Lewis acids and bases. Okay. So, first is Arrhenius scientist. Second is Bronsted and Lowry, 2 scientists, and third is Lewis. So, these 3 scientists, they are going to give, they have already given the definition for acid and base. Okay. So, we are going to learn those definition according to each person's point of. Okay. So, let's move on to the first concept, Arrhenius concept of acids and bases. So, this person is Arrhenius. Okay. And he said that acids are the substance, or they get dissociated in water to give hydrogen ions. Acids are the substance which gives H plus ions. Okay, and bases are the substance, or the bases dissociates in water to give hydroxyl ion. Okay, the H plus ion producing substances are called as acids, and OH minus ion producing substances are called as bases. This is the definition for acid and base according to Arrhenius. Okay, and there were some limitations in this concept, and because of this, is actually acids and bases. Okay, yeah, and because of the limitations that has been arised in his theory, so the second scientist, Bronsted and Lowry, these two people have come up with their own ideas. Okay, he is Bronsted, Johannes Bronsted, and this person is Thomas Lowry. Okay, so these two scientists, they came up and they said that acid is a substance that is capable of acid is a substance that is capable of donating a hydrogen ion. Base is a substance that is capable of accepting a hydrogen ion. So here they did not involve OH minus at all. They are giving the definition in terms of H plus itself. Okay. So H plus donor are called as acids and H plus acceptor are called as bases. We can redefine this definition. Like acids are proton donors. Protons are nothing but H plus, right? Acids are proton donors and bases are proton acceptors. So this is their definition. And we will see some example for this. Okay. So here is an equation. Here is an equation. So NH3 is a base, ammonia is a base, and H2O is an acid. Okay. Now ammonia has taken one hydrogen from water and it has produced NH4 plus and OH minus remains there. Okay. So here you see adds to this NH3 we have added one proton. H plus has been added, so it adds proton. And now this NH4 plus is the conjugate acid. NH4 plus is called as the conjugate acid. Positively charged species are called as acids. Okay, and here is the conjugate acid of NH3. Okay, now OH minus is that H2O is losing the proton, right? So it loses that proton, and that's why it has formed like OH minus. And this OH minus is the conjugate base. OH minus is the conjugate base of H2O. And here H2O is called as Bronsted-Lowry acid and NH3 is called as Bronsted-Lowry base. The substance which is donating the H plus is called as acid and the substance which is accepting the H plus is called as base. So is this clear to all of you? Any doubt from this? Any doubt from this? No, clear. Fine. So we will see one more example. So HCl and H2O. HCl is called as an acid and H2O is a base here. Okay. So here HCl is losing one proton and it is becoming like Cl minus. So Cl minus is a conjugate base. And H2O is accepting the H plus. So H plus is added over there. So it is the conjugate acid. Now in this reaction, HCl is the Bronsted-Lowry acid and H2O is the Bronsted-Lowry base. So in both the reaction, if you see, in one of the reaction, water is acting as an acid and in the second reaction, it is acting as a base. So the substance which can act as an acid as well as a base, it is called as an amphoteric species. So water is, H2O is an amphoteric species because it acts as both acid as well as base. Clear? So this is about Bronsted-Lowry concept. Now in this theory also, in this concept also, there were some limited, it was applicable only to very limited compounds. Okay. So because of the limitations, thirdly, this Lewis scientist is coming. Okay. G.N. Lewis, he is coming up with his own idea and his definition for acid was acids accepts the electron pair and bases are the substance which donates the electron pair. So this person doesn't talk about H plus or OH minus or anything. He is talking about the electron pair. The substance which is accepting the electron pair is acid and which donates the electron pair is called as base. Now I'll give you an example. BF3 and NH3. BF3 and NH3. Now here if you see, there is a bond formation between this BF3 and NH3. This is actually a bond. Okay. And here I can write like this also. BF3 is accepting the electron from NH3. So this is the bond. So both the electrons are coming from the nitrogen of ammonia. So this bond is called as coordinate covalent bond. Okay. So this nitrogen NH3 is donating its electron pair So that's why it is called as a base. And this BF3 is accepting the electron pair from this NH3. So BF3 is called as acid. Clear? I'll give you some examples for Lewis acids and bases. Yeah. AlCl3, CO3 plus, magnesium 2 plus, all the metal ions, they are falling under Lewis acids. And since this aluminium belong to the group 13, mostly the group 13 elements will behave as a Lewis acid. This boron is also a Lewis acid because boron is a 13th group element. Okay. And coming to Lewis bases, if you see the lone pair containing elements, oxygen has 2 lone pair, nitrogen has 1 lone pair, and the negatively charged species, they will fall under this Lewis bases category. Okay. These are some of the examples of Lewis acids and bases. So any doubt from the 3 acid-base theories, from Arrhenius, from Bronsted-Lowry, and from Lewis? So in Lewis theory, there is no limitation. There is no disadvantage that has been observed in Lewis theory. So we are till now we are following this only. Okay. Thank you, Shamila. Yeah, good. Yes, good, Hashira. So now we will go with the next topic. Self-ionization of water. So self-ionization. So in this picture, you can see we have taken 2 water molecules. Okay, one is acting as an acid and the other one is acting as a base. And here you see the first molecule is acid and the second molecule is a base because the second molecule is accepting one H plus from the first molecule and it is producing this H3O plus. And since this first molecule has donated his H plus, it is having only OH minus, so it is called as a conjugate base of the first molecule. Okay. So 2 water molecules are undergoing self-ionization. So that's why it is called as self-ionization of its own substance, that is water. And if I want to write the equilibrium constant for this reaction, I will be writing like this. Yesterday I have taught you know that how to write the equilibrium constant. It is the product of product concentration divided by the product of the reactants concentration. Okay, since both are water here, the reactant is a water, so that's why it has gone to the denominator. Now, if I take this H2O to the other side, I will have K into the concentration of H2, right? This K into the concentration of H2. This together, K into concentration of H2O together is called as KW. It is called as KW and that is equal to this H3O plus concentration, OH minus concentration. Okay. At 298 Kelvin, this KW, which is called as ionic product of water, it will be equal to 10 power minus 14 mole power 2 and okay, this is very important. At 298 Kelvin, the Kw ionic product of water, this is ionic product of water, that is equal to 10 power minus 14. Okay. Now we'll see some more information about this. Now this ionic product of water Kw, it is equal to this concentration of H3O plus and OH minus. Since the concentration of these 2 ions are going to be same here in this case, I can substitute H3O plus in place of OH minus, right? So if I substitute H3O plus in place of OH minus, I will have 2 H3O plus. So it is getting the square here and now it is going to be to 10 power minus 40. Okay. So from this, the concentration of H3O plus can be found using like this, that 1 into 10 power minus 7. Yes, good. 1 into 10 power minus 7. If I take the square root, I will get 1 into 10 power minus 7. Okay. So these are the informations about the self-ionization of water. Got it? Now we will solve one question. A solution in water has a hydronium ion concentration of 2 into 10 power minus 6 molar. And what is the concentration of hydroxide ion? Hydronium ion is nothing but H3O plus or H plus ion. Okay. And that concentration is given. We have concentration at 25 degrees Celsius. How to solve this? What is 25 degrees Celsius? It is nothing but 298 Kelvin, right? It is nothing but 298 Kelvin. Now, we know that The ionic product of water at 298 Kelvin is, what is the value? What is ionic product value? So this is the equation. Yeah. At 298 Kelvin, Kw, ionic product of water, is equal to 10 power minus 14. So therefore, OH minus will be equal to Kw by H3O plus. Okay, Kw by H3O plus. And here Kw is 10 power minus 14. Just substitute the value over here. Okay, substitute the value over here. And H3O plus ion concentration. It is given in the question, right? Hydronium ion, which is nothing but H3O plus. So just substitute 2 into 10 to the power minus 6 in that place. And if we solve this, we will get 5 into 10 power minus 9 mole per liter. Just direct substitution. Direct substitution. So is this a problem, numerical part, clear to all? Shall we continue with this self-ionization of water with some more information? Yes or no? Yes. Okay. Yeah. So I have taken a beaker and it has H plus ion concentration, OH minus ion concentration. So 2 H plus I am having and 2 OH minus I am having. So the number of H plus ion and the number of OH minus ion, they are equal. If it is equal, then the substance is neutral because the concentration of both ions are same. And we know that the concentration of H3O plus or H plus is 10 power minus 7. And we also studied one formula, right, about the pH. How to calculate the pH from H plus? pH is equal to, we already studied, in our lower classes we have studied. pH is equal to minus log of H plus ion concentration. In place of H plus, you can substitute H3O plus also. Both are same. H2O and H plus is nothing but H plus. Okay. So it is equal to 10 power minus 7. So yeah, here is the formula. pH is equal to minus log of H3O plus. In place of H3O plus, substitute 10 power minus 7. If you substitute 10 power minus 7, what you will get? pH will be equal to 7. You all know that formula, right? Log of m to the power n. It is n into log m. So here m is 10 and n is minus 7. So n is minus 7 and log of m is 10. Log 10 is equal to 1. So we are getting minus 7 and already we are having one minus here. So it becomes plus. So the final answer is 7. Final answer is going to be 7. And if the pH is equal to 7, we all know that the substance is neutral. And this is how we are proving that. Now coming to the second case, here we have 3 H plus ion and 2 OH minus ion. So the number of H plus is more, means the compound is acidic in nature. Compound is acidic in nature. If the compound is acidic in nature, pH will be less than 7. Okay. And the third case you know very well, right? OH minus ion is more than H plus. Means the substance is basic. If it is basic, pH will be greater than 7. pH will be greater than 7. So this is a concept that we are getting from the self-ionization of water. Okay. So let's move on to the next thing. There is an issue. Yeah. Now at 298 Kelvin, we know that Kw is equal to 10 power minus 4. If I take pKw, like pH, if I take pKw, it will be equal to 14. It will be equal to 14. So pH plus pOH is equal to 14. This is one of the very important formula. Okay. And this ionic product Kw, it depends on temperature. It depends on temperature. We already studied, right? At 298 Kelvin only, Kw is equal to 10 power minus 14. If we increase the temperature or if we decrease the temperature, it will also change. So Kw is temperature dependent. So the equation is applicable only at 298 Kelvin. If in the question, if you're having that 25 degrees Celsius or 298 Kelvin, only in those questions you can apply this value and get the answer. Okay, for the other reactions you cannot do. It is it is a mathematical operator, like how we are having plus for addition and minus for subtraction. pH is nothing but the operator which operates on this H plus. Okay. Potential of hydrogen we are saying no in the same way. pKw. Okay. So this is the important formula. And the third next topic is buffer solution. Third is buffer solution. So what is a buffer solution first of all? A solution which resists the change in pH, and pH does not change significantly on addition of small amount of strong acid or strong base is called as buffer solution. So I am having one solution, and if I try to add an acid to the solution, or if I try to add a base to that solution, the pH of the solution will still remain same even after the addition of an acid or a base to the corresponding solution. Okay, so those solutions are called as buffer. They resist the change. They resist the change in pH even after the addition of small amount of strong acid or strong. If I am adding a strong acid, pH of the solution should decrease, right? And if I'm adding a strong base, pH has to go higher, but they remain same. Okay, those solutions are called as buffer. And here we have two types of buffer solution. One is simple buffer solution and the second one is mixed buffer solution. The first is simple buffer. Oh, so it is an aqueous solution of weak acid and weak base type of salt. For example, you see ammonium acetate, ammonium cyanide, and silver cyanide. These are the examples. So weak acid and weak base. So you can take CH3COOH as an example for weak acid and NH4OH as an example for weak base. Ammonium hydroxide is a weak base and acetic acid is a weak acid. Okay, and if I react these two, I will get CH3CO minus and NH4 plus, right? I will get ammonium acetate. And this is a salt. I'm getting this salt. And this salt is a combination of a weak acid and a weak base. Okay. So these are the examples. And if we want to try to find out the pH of weak acid and weak base, we have to use this formula. 7 plus 1 by 2 pKa minus 1 by 2 pKp. Okay. Very important formula which has to be used for weak acid, weak base. Previous slide you need. Okay. Shamila, is this the slide you were asking? Okay. Okay, take a note of it. Let me know once you are done with it. Have you completed? Okay. So we have completed the simple buffer concept also. Yeah, then we will move on to the mixed buffer solution. Okay, mixed buffer solution. And in mixed buffer, we have two types. One is acidic buffer, the other one is basic buffer. Buffer solution which has pH less than 7 are called as acidic buffer, which has more than 7 are called as basic buffer. Acidic buffer is a combination of weak acid and its salt with a strong base. Very, very, very important. Okay, acidic buffer is it is prepared by mixing a weak acid and its salt with a strong base. You see the example here. Acetic acid is a weak acid and it is a salt. And this salt has been formed from weak acid and strong base. CH3COOH is a weak acid and NaOH is a strong base. This is a strong base and this is a weak acid. And if these two react with each other, it will produce CH3COO minus and Na plus, right? So this is a salt which has formed from a weak acid and a strong base. Okay, it is a weak acid and its salt. It means weak acid. It means weak acid salt with a strong base. This weak acid salt with a strong base. Got it? Very important. If I have to find out the pH for acidic buffer, I have to use this relation pKa plus log of the concentration of the salt by the concentration of acid, or the concentration of conjugate base divided by the concentration of acid. And this reaction, this equation, this formula is called as Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. Okay, both the equation. So basic buffer equation, acidic buffer equation. These two equations are called as Henderson-Hasselbalch equation, which are being used to find out the pH and pOH of an acidic buffer and basic. Basic buffer is prepared by mixing weak base and its salt with a strong acid. Ammonium hydroxide is a weak base and its salt, ammonium hydroxide salt with the strong acid. So what I have to take? I have to take ammonium hydroxide and strong acid. The example for strong acid is HCl. You can take HCl. If these two react with each other, it will produce NH4Cl, right? So this is a salt from weak acid, from weak base. This is a weak base and a strong acid. Okay. So in this entire ionic equilibrium lesson, we will be using strong acid, strong base, weak acid, weak base. Okay. In all the concepts, you can fix or you can keep HCl as an example for strong acid, and NaOH as an example for strong base, CH3COOH as an example for weak acid, and NH4OH as an example for weak base. Okay, just keep these as an example for each term. Then only you will not get confused. Okay, we have many strong acid, many strong base, but keep this in mind. You will not get confused in the concepts. Clear? And to find out the pOH, Henderson-Hasselbalch equation for basic buffer, that is pOH is calculated using pKb plus log of the concentration of salt by the concentration of base. Clear? Clear for all? Shall we move on to the next topic? Yes? Okay. The last topic, the last topic for today's session is solubility product. A solubility equilibrium exists when a chemical compound in a solid state is in chemical equilibrium with the solution of that compound. What we are having one compound that is in solid state and it is going to be in chemical equilibrium with the solution of that compound. What is the meaning for that? Let me explain this with an example. Barium sulfate I have taken. Barium sulfate is a salt. It is in solid form now. You see here it is in solid. Now, if I put this in water, what happens? Ba2 plus ion and sulfate ion, SO4 minus ion will come out, will get dissociated. Now they are in aqueous form. Now this aqueous form of this compound and solid form, they are in equilibrium with each other. They are in chemical equilibrium with each other. Okay. So this is called as solubility equilibrium. So the initial concentration of the reactant is taken as S and there is no formation of product. So the initial concentration of Ba2 plus SO4 minus is 0. And after some time, they attain the equilibrium, right? So the equilibrium concentration for the product is S and S because we have only one Ba2 plus and one SO4 minus. You see here, the number of ions produced is 1 and 1. So it is S and S. So if I want to write the equilibrium constant for this reaction, what I have to do? Equilibrium constant is nothing but the product of the product concentration divided by the product of the reactant concentration. So the products are Ba2 plus and SO4 minus. The reactant is BaSO4. Now take this BaSO4 to the other side. We will get K into the concentration of barium sulfate. Okay. This K into the concentration of this barium sulfate is represented as KSP. And this KSP is called as solubility product. Okay. For barium sulfate, the solubility product will be approximately 1.1 into 10 to the power minus 10. It is equal to, just substitute. Ba2 plus concentration is S and SO4 minus concentration is also S. Just in those place, you just substitute. So it becomes S square. So from this, if I have to calculate S, what I have to do? I have to take the square root of 1.1 into 10 power minus 10, right? If I take that, I will get 1.05 into 10 power minus 5 mole per liter as the solubility value for this barium sulfate. Clear for all? Is this clear? Shall I explain this with one more example? Shall we see one more example? Yeah. Yeah, the second example is calcium phosphate. So in calcium phosphate, if we dissociate this, we will have 3 calcium ion and 2 PO4 3 minus phosphate ion, right? So the initial concentration of the solid substance is yes. The formation of product, they are 0. Concentration of product is 0. And at equilibrium, there is no reactant concentration. And here we are having 3. So it is 3S. And here we are having 2 phosphate. So it is 2S. This is actually 2S. Okay. This is 2S. Now, the KSP will be calcium 2 plus power 3 and Q4 3 minus power 2. And we are putting these coefficients to the power. Okay. So what I have to do for calcium, for this calcium ion 3S and for phosphate ion it is 2S. So in place of the concentration, you substitute 3S and 2S. If I substitute here, what I will get? 3S, 1 cube is there. So I have to put this cube and 2S square. Okay, it's 2S square. And if we solve this, 3 cube is 27, S cube into 4 into S square. 27 into 4 is 108, S power 5. So clear for all? Shall I give one more salt? Will you solve? Shall we try with one more salt? Okay, I'll give you one salt. You guys try and give me the KSP value. Okay, which salt we can take? Okay, I'll give you calcium chloride. Can you find out the solubility product for calcium chloride? Let me see who is finding out the answer first. I'll give you 30 seconds. 30 seconds is enough to solve this. Try to solve this. Has anyone got the answer? Okay, I will do here. Meanwhile, if you have completed, put the answer in the chat box. Okay. So now, if we try to dissociate this, we will get 1 calcium 2 plus and 2 Cl minus ion, right? So here you see we are having only 1 calcium 2 plus and 2 Cl minus. So it is S and 2S. If I have to write the KSP, what I will get? Calcium 2 plus concentration into Cl minus concentration power 2. So the calcium concentration is is S and Cl is 2S power 2. So it is S into 2 square is 4S square. So the answer is 4S power 3. So this is the KSP value for calcium chloride. So is this clear for all? You need to know the dissociation. That's it. If anything, any salt is given in the formula format AX and BY, how we will do? It is X into A power Y plus and Y into B power X minus. So this is the formula, right? This is the formula which we are using from our lower classes to find out the number of ions produced. If I'm having some other salt, if I'm having aluminium 3 plus, how to dissociate? Aluminium is having aluminium 1 and Cl3. So X value is 1 and Y value is 3. So it is 1 aluminium 3 plus and 3 Cl minus. So this is how you have to dissociate. Clear for all? Yes. So now use this part. This solubility is very easy and it is very important also. Okay. So suppose in the question, they can give this KSP value and they will ask you to find out the S. So in that case, you have to take the square root or the cube root. Okay. So that thing you have to take and give the answer. Either one of this KSP or S will be given to you in the question and you have to find out the other term. So that is very important. This direct substitution. Now we will see the application of solubility product. So first it is used to find out the solubility. This is what I was talking about. We can find out the solubility S from this solubility product. Suppose for mono, tri-valency type of salt like NaCl. NaCl is mono type, right? And BaSO4 is also mono. And CH3CO minus Na plus is also the same thing, AB type only. For any AB type of salt, the dissociation is A plus and B minus. And in that case, we have SS for both. So it will be S square or S is equal to square root of KSP. Okay. This is how we have to find out the solubility. Then for the second type, KSP for AB2 type, AB2 type or A2B type. So here calcium chloride is AB2 and this is also AB2 and this is A2B type, right? And for this type, you have to dissociate A2 plus and 2B minus. It is S and 2S. In that case, we have got 4S cube. For calcium chloride, we have tried now, right? So we have got 4S cube and S will be equal to KSP by 4 power 1 by 3. Okay. So this is how we have to find out the solubility. Now coming to one more small topic, that is hydrolysis of salt. Hydrolysis of salt. So any doubt any of you have from the solubility product? Is everything clear for all? Shall we discuss the hydrolysis of salt? Yes. Yeah. The salts of strong acid and weak base, weak acid and strong base, weak acid and weak base. What are the three combinations? Strong acid and weak base, weak acid and strong base, weak acid and weak base. Okay. So these three combination salt, they undergo hydrolysis in aqueous solution. They undergo hydrolysis in aqueous solution. And here you see one combination is missed out. So, strong acid and strong base is missed out, you see. Strong acid and strong base we don't have here. So the salt of strong acid and strong bases do not undergo hydrolysis. Okay? Because if I take a strong acid, for strong acid we can take HCl as an example and strong base it is NaO. If I take these two, they will produce one salt and that is NaCl. Okay? The salt of this, they do not undergo hydrolysis. So the pH of the solution will be equal to 7. pH of the solution will be equal to 7. Okay. Now if I have to if I want to find out the pH for the first combination, that is for strong acid and weak base, if I want to find out the pH, I have to use this formula 7 minus 1 by 2 to pKb plus log C. C is nothing but the concentration. And for the second combination, for strong base and weak acid, for the strong base and weak acid, I have to use the same relation. Instead of minus, you put plus. The third relation is weak acid and weak base. For this, 7 plus 1 by 2, pKa minus pKb. So these are the very important three formulas that we will be using for solving all the numericals that is coming from hydrolysis of salt water. Clear? Then, with all these concepts, with this the lesson gets over. Equilibrium lesson gets over with this. Now, using the topics that we have discussed today, we will solve some previous year's questions. Because chemical equilibrium and ionic equilibrium, it is a physical chemistry lesson. So we need to see some questions. Then only we will be able to understand. So the first question is to you on the screen. It is a straightforward question, right? An acidic buffer is prepared by mixing. Can anyone give me the answer for this question? It's very easy, no? When I was discussing the buffer, I told you, right? Acidic buffer is a combination of what and what? Dash and dash. Which option is correct? D. No, D is not the answer. Just go through your notes, you will get the answer. Option A. Acidic buffer is a combination of weak acid and its salt with a strong base. I also have taken the CH3COOH as an example, right? And I have explained you know it is CH3COOH plus its salt with a strong base. So this is the example for acidic buffer. You should not forget. Don't get confused. Learn properly. Okay. Then coming to the next question. 0.01 molar acetic acid solution is 1% ionized. Then pH of this acetic acid solution is, for weak acid, acetic acid is a weak acid, right? For weak acid like this acetic acid, formula for acetic acid is CH3COOH. The H plus ion concentration, it can be calculated using one formula. You can take down this formula. It is C into alpha. It is C into alpha. C is concentration. Alpha is the degree of dissociation. Okay. What is the concentration? Concentration is 0.01 molar. And the degree of dissociation or ionization, both are same only. It is 1% ionized. 1% means how I have to write? It is 1 by 100, which is equal to 10 power minus 4 molar. The concentration of H plus, that is 1% ionized, is 10 power minus 4 molar. Now I have to find out the pH of this acetic acid. What is the formula for pH? pH is equal to minus log of H plus ion concentration, right? So substitute minus log of, what is the concentration of H plus? 10 power minus 4. So here it will be equal to, the pH will be equal to 4. The pH is equal to 4. Log of m to the power n formula you have to use. So the answer is 4. pH is 4. So is this question clear? Shall I move on to the next question? Yes? Okay. The pH of the solution containing 50 ml each of 0.10 molar sodium acetate and 0.01 molar acetic acid is. Acetic acid is a weak acid and sodium acetate is a salt of weak acid and strong base. Right. What is the formula for sodium acetate? CH3COO minus plus. This is weak acid and this is from strong base. So for this, we have to find out the pH. So what we have to use? We have to use that Henderson-Hasselbalch equation which I was talking about. Henderson-Hasselbalch equation you have to use. For this salt of weak acid, strong base and weak acid, the Henderson-Hasselbalch equation is pH is equal to pKa plus log of conjugate acid, concentration of conjugate acid. I'm sorry, it is the concentration of conjugate base. To find out the pH, we have to use base in the numerator. It is the concentration of conjugate base by concentration of acid. Okay. Now, what is the pKa value? It is given in the question. So, it is 4.57 plus log of, who is the conjugate base? The sodium acetate is nothing but the conjugate base and its concentration is 0.1 divided by, and acid. This is the weak acid and its concentration is 0.01. So how I can take this? I can write this as 10 power minus 1 by 10 power minus 2, right? So it goes off 10 power minus 1 we have. If it goes to the numerator, it is 4.57 plus log of 10 to the power 1, log of 10 1. So it will be equal to 4.57 plus 1. It is 5.57. So the pH for the acetic acid is 5.57. Option A is the answer. Option A. Just you have to apply this straightforward formula to arrive at the answer. That's all. You need to find out which is given in the question. How to extract the given information from the question. And if you try to abstract that information, and if you have found out the formula that we have to apply for that particular question to solve it, you can get the answer easily just by doing very simple calculation like this. Okay, clear? Shall we do one? What is the time now? It's 3:55. Shall I do one more question? Okay, yeah, we will close the session with that question. The pKb of dimethylamine and pKa of acetic acid. This is acid and this is a base. They are given. The correct option for pH of dimethyl ammonium acetate solution is. So this compound is a salt. It is a salt of weak acid and weak base. Ammonium acetate. Ammonium hydroxide is a weak base, right? And acetate is from acetic acid. Acetic acid is a weak. So it is a salt of weak acid and weak base. For this, we have to find out the pH. For weak acid and weak base, what is the relation to find out the pH? At last, I have given you 3 relation, right? In that, 7 plus 1 by 2 pKa minus pKb. This relation, first relation we have to use. So it is 7 plus 1 by 2. What is pKa? pKa is for acid. It is 4.77 and pKb. For base, it is 3.27. And if we solve this, we will get 7.75 as the pH value for the given solution. Okay. So which option is correct? Option D is the correct answer. Clear for all? So this is enough for today. So I hope this is equilibrium concept is clear to all of you. So we will try to solve some more questions on this also. I think in this weekend class or maybe in the next weekend class, the other sir will discuss the questions of equilibrium lesson for you. So you can practice from that session. Okay. So if you are having any doubts, you can ask me. If there are no doubts, we will meet in the next session with a new lesson. Okay. We'll meet up in the next session with a new lesson. Till then, take care. Thank you so much for listening to today's lecture. Take care. Bye-bye. So nobody's having any doubt? Okay then. Thank you, students. Bye. Okay.